Hide that down there. And today's lesson is on the structure of the atom. You can see it there, atomic structure. And the first thing that we're going to talk about here is the atom itself. Oh, and I'm going to back up here because I'm going to draw on the smartboard. I'm going to draw that atom there. So, on Friday, we talked about the elements and some of their properties, but we didn't talk about how the atom is built itself. And so today we're going to be dealing with the atom itself. What are the pieces of the atom? What's in the atom? How do we draw the atom? Okay? And how do we analyze the parts of the atom? I believe in our discussion that we've had in the past classes that for many of you, this is not new information. I get the impression that many of you remember from grade 9 these 3 particles that are found within an atom. In my grade 11 university course, I talk in great detail about how these particles were discovered. The electron was the first one to be discovered in the late 1800s. Late 1800s. Scientists knew of electricity, and they knew of electricity since the late 1700s. What's his name? Who did the flying kite experiment? Why can't I think of it? Ben Franklin? Ben Franklin? He realized that static electricity was really just like in lightning. It's the same thing. Actually, they knew about static electricity for many years. Like even the ancient Greeks knew about static electricity. It wasn't until a guy by the name of Alexander Volta created the first battery, and then they got working on what is this electricity. And in the end, they realized that the electricity was actually caused by these electrons. The proton wasn't discovered until the early 1900s. A guy by the name of Ernest Rutherford discovered the nucleus, and in the end they found the proton. The neutron was very hard to find. The neutron is very hard to find because it doesn't have a charge. It's neutral. I think you guys all know that. That's what that little 0 stands for. It means it doesn't have a charge. And particles that don't have a charge are very difficult to study because you can't move them around with charges. Here, these guys you can move around. Anyway, okay. So in my picture, I'm going to have a couple of different particles in the center. So I'm going to start with a couple of red dots. You guys can just put them as dots, right? And then actually, I'll keep the color the same. I'm going to put circles to represent the other particles, and I'm only going to put 4 particles in that center part. All right, and in that center part, what do we call that center part of the atom? Yep. The nucleus. Excellent. So I'm going to put that down here. That is the nucleus, actually named by that scientist by the name of Rutherford. And in the nucleus, we have the protons and the neutrons. So you can imagine that the solid dots are the protons and then the circles are the neutrons. However you want to do that, that's up to you. And so therefore the nucleus is positive. And it's very small. I'm going to put down here, very small. Okay? Where do the electrons go? Anybody know where the electrons go? Yep. Yeah, they orbit around it. So I'm going to take a different color here. I'll take blue, and I'm just going to put a circle around this guy here. Blue is not very good. It's hard to see, but it's not bad. And I'm going to put a little dot up here. And I'm going to put a little dot down there because I've got 2 electrons in this atom. 2 electrons and 2 protons and 2 neutrons. And I'm going to take the yellow and I will just write over here that this is the E negative or the electron. All right, and we're going to say that the electron is in orbit. Okay, it's going around there kind of like planets go around. Excellent. Like I said, the nucleus is very small. If you were to try to represent the actual relative sizes of the nucleus when it comes to the size of the orbit, if we were to use our track as being the orbit, you know, the track out back there, 400-meter track, if you were to use the track as being the orbit, you would need essentially a pea, you know what I mean, like the vegetable, a pea, at the center of the football field to represent the nucleus. That's how small it is. It's incredibly small. Okay, the nucleus is phenomenally small. Okay, does anybody know what kind of atom this is? I've actually drawn a representation of an actual atom. I've put 2 protons in the nucleus. It happens to have 2 neutrons, and it has 2 electrons in orbit. Yep. Yeah, that's correct. This is a representation of a helium atom, right? Because that number right there is the atomic number. We're going to talk about that in a moment. And what does that atomic number tell us about the atom? It's how many electrons if the atom is neutral, if it's not a charged atom. This is also the same. There's another number of particles that's also the same. Yep. Yeah, it tells us the protons. The neutrons can vary. In this particular element, they're all 2, 2, and 2. But that doesn't have to be the case. You can have nuclei that have more neutrons than protons and more protons than neutrons. There's nothing special about that number of neutrons. It can vary, okay? All right, let's take some more information here. Oh, don't mind that picture. Mine's much nicer than that. Okay, there we've got wait a minute, I've already done this. Hold on one second. Found the nucleus. We've done this. Same mass as the protons, neutral. Found the nucleus. Electrons. Hold on, don't write this down. Negative. They're found in orbit. Do we have anything missing from our previous slide that's in those statements? Let's put with the protons, write down that they're heavy. So on your note with the protons, write down that they're heavy. And that's going to go with the protons and the neutrons. Okay? No, so write down there with the protons, write down that they're heavy. That's it. Just write down that the protons are heavy. It's true that the neutrons are the same mass as the protons. They're the identical mass. You don't need to write that in. With electrons, though, I would like you to write that they're very small and very light. All right? So with the electrons, up there where it says electrons, write down that they're very small and very light. They're a very, very tiny little particle. I think we've indicated that the protons are positive. There's a plus up there, right? We've indicated that the electrons are negative, and that 0 that we put with the symbol N represents that it has no charge. It's neutral. And I think we've got that information. I don't think we need to write that. Are we good? We've got what we need on that picture? I think so. We're adding anything there? We're good? I just see Zach writing. He's just finishing off this. You got your information? No rush, no rush. Okay. All right. So let's now then talk about the atomic number. The atomic number. And we've briefly discussed this just moments ago. So all this information we've talked about. The atomic number is the number of protons in the nucleus. It is the number of electrons in the neutral atom, if the atom was neutral. After our test, we're going to talk about something called ions, which are charged atoms, and they're charged when electrons leave. So the electrons can come and go. The protons can't come and go. But for now, we're going to just talk about a neutral atom, one that has no charge, good old regular atom. The atomic number also identifies the elements. Now, I've been making reference to the periodic table. And I've also been, I also gave you kind of a copy of the periodic table. But when we write tests, this is the periodic table that I'm going to give you. So I'm going to give you all a copy of this table just so that when I'm talking about things, you can follow along and take a look. You're going to give these back to me at the end of class. And like I said, these are ones that I would give you to use during tests. 1, 2, 3, 4. But for now, I'm just going to have you look at this because I know that that periodic table that I'm pointing at is far away, and sometimes it's hard to see the numbers. So don't worry about the back. Don't worry about the data on the back there, Max. We're looking at the front. When you're looking at the periodic table, and when I'm looking at my periodic table, the atomic number is represented by this big red number that's in the corner. All right, you can see it there. Your atomic number, I believe, instead of being in the right corner, is in the left corner. Does everybody see the atomic number there in the left corner? So if you take a look at the helium atom, all right, which is this one right there, you'll notice in the upper left-hand corner there's a number 2. Everybody see that number 2? And if we move across then to the lithium atom, you'll notice there's a number 3, indicating that lithium has 3 protons, beryllium has 4 protons, boron has 5 protons, etc., etc., etc. Are we okay with that idea? Now there's other numbers on this table as well that we're not going to use, but I'm just going to point them out. Underneath the symbol in my table, and for yours it's in the right-hand corner, is the mass. That's the mass of the atom. So again, if we look at helium, mine says 4.00260, and I'm hoping yours says the same thing, 4.0026. You just don't have a 0 on the end. We're not going to worry about the mass of these atoms in this class. You don't have to worry about that. You can determine how many neutrons there is using that mass, but we're not doing that in this course. So the mass comes from the protons and the neutrons, but don't sweat about it. Okay, it's not a big deal. Your table also has a couple of other things underneath there, and that's the charge. That's at the bottom, and there's a couple of other numbers, but we're not going to use those numbers. The only number we're going to use here today is that atomic number, which tells us how many protons are in the nucleus. Like this says, it also identifies the nucleus, it identifies the element, and we identify the element with a symbol. So if I know I'm dealing with an atomic number of 2, I know that I'm dealing with a helium atom. I know I'm dealing with He, and now I know the chemical properties. I know it's a noble gas. Okay, so it identifies what it is. All right, so let's just do a little practice run here. You don't need to make a box in your notes. At this point, just make a grid like I said the other time. Just make a quick and easy grid. It does not have to be fancy in any way. And let's practice getting some information. Again, I would put one line across there, and then I would just use the lines on my page to do the rest. Now, I teach the university level chemistry, grade 11 and 12. and I haven't taught this course in a long time. But when I get to this grid here, and I start looking at the title, atomic number, okay, the number of protons, all right, and then the number of electrons, okay, we're talking about the atom. I sometimes think I'm insulting your intelligence because you guys are pretty bright. You guys have been answering really good questions. What's true about the atomic number, the number of protons, and the number of electrons? Yep, they're all the same. So, like I said, I feel like I'm insulting your intelligence. What's going to be true about all these numbers across these 3 grids? They're going to be the same. So I'm hoping you're looking down there right now and, you know, filling it in like crazy. Because the protons are the same as the atomic number. And if we're talking about a neutral atom, it's the same number of electrons. So right away, if we're trying to get this done, because I know you guys sometimes like to get things done quickly, we're doing this type of thing. It's all the same. This thing's got 82, oops, mess. 82 82, 20, 20. I guess the hardest work is figuring out what those elements are. You guys have a table right there. What's 28? Yep. Is it nickel? N-I. Capital N, lowercase I. 28. Next one. Sorry? Is it lead? 82. We don't like it. I got a no there. Let's take a look. Yeah, 82. I like it. PB. Anybody remember why it's got a symbol PB? Yep. You can say it. You can say it. It's plum bum. Don't be afraid. Yeah. Oh, okay. I thought maybe you were afraid of putting the word plum with the word bum. Right? Yes. Oh, you got the last one? Calcium, Ca. What is my information for gold? Is it 79? 79, 79, 79. So like I said, you know, sometimes when we set this up, we don't give you guys enough credit. All those numbers are all the same. The atomic number, the number of protons, and if the atom is neutral, which is what we're dealing with today, we've got that. Okay, so now we're going to do something called Bohr diagrams. So I do want you to write this down, and you don't necessarily have to. Yeah, you can write this. This is what I would do is just put a circle in the middle, and then let's put some circles, and then 18. We're never going to get to the fourth orbit. And that's a little misleading. No, we'll leave it. We'll leave the 18. No, there is 18, but we don't ever draw Bohr diagrams for that fourth level. So yes, I do want you to write it down, and then I'll show you what I'm going to get you to draw here. We now know that those orbits don't cross over each other.
Okay.
You don't have to change it. It's okay. But we now know that they all travel in circles that have a certain number of electrons in them.
Okay.
All right? But you don't worry about changing it. But that's the way we represent that now. Like circles like that. Right? So what do I want you to do with this picture? Right, I would with your pencils, I'd draw some of these orbits in here. All right, and I do want you to draw 1, 2, and 3. I guess I didn't need to put it over top of these others, but that's okay. And I'm going to put some dots on here to represent the electrons. When we start drawing our Bohr diagrams, you only put 2 electrons in the first orbit. All right? So this is not the orbit. This is the nucleus. Inside the nucleus, we're going to put the number of protons. So in your circle, just put their number of protons. Oh, we've already done that. Nice. We're not going to worry about neutrons this year. So we're just doing protons. Okay? I like to put the dots together in the first orbit. Some teachers might have had you put it on opposite sides. I've taken a lot of chemistry, and scientists know that when there's not enough room, the electrons will pair up. They will form a pair. So I draw it that way. When we draw the electrons in the second orbit, where there's 8 of them, I always start by drawing 1 by itself, then 2 over here, then 3 down here, and then 4 over there, like a clock. And then when I have to add a 5th, I pair it up. And then if I have to add a 6th, I pair it up again. A 7th, pair it up. And then an 8th, pair it up. Yep. No, you won't. But if you are planning on continuing on in chemistry, say you want to go on to the college chemistry because you're interested, say, in the CPET program, you know what I mean, at Lambton or that type of thing, understanding the way those electrons go will make your knowledge of being able to talk about things like bonding easier. Because again, that's the way it actually takes place, and it is a very useful way to explain the way they bond later on. So it'll make your life easier if you think of it that way. That's why. But if you're on a test and you just put dots around it, and I'm just marking to see that you got enough electrons in that right orbit, I would give you full marks. But what I'm trying to do is I'm trying to prepare you for the next time when we start talking about bonding, okay? So the easy way to think about it, when you think about an orbit that has 8, is to think of it like a clock, 12, 3, 6, 9. The 4 electrons, they spread out as much as they can, but when you get to 5, they're forced to pair up, all right? So then, again, 6, 5, 6, 7, and then 8. And that's just to keep things easier for when we continue on in the future, okay? We're not going to worry about the 4th orbit. I've seen some teachers, you know, they'll do something like cobalt, and just have the kids put a whole bunch of dots in there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever it is. But if I'm teaching you about the way to position these here, I'm not going to bother teaching you this because they don't just go around and unpair. It's very complex. Even in the grade 11 university chemistry, we don't talk about where electrons go here because the students don't have enough information on it. I have to teach a subject called quantum mechanics that is used to explain where these electrons go. Very complex. We won't be drawing Lewis diagrams for those. Okay, so at this point, don't draw this. What I'm going to get you to do is, I want you to go to Google Classroom. So I'm going to switch as well. Uh-oh, I shut off my monitor, but I think we're still on. Google Classroom. Oh, I didn't open Google Classroom. Why am I so dumb when it comes to opening the page? I don't even have a web browser open. Terrible. All right, let's skip out of this. You guys go to Google Classroom and you're going to open the sheet on Bohr diagrams. All right? So you're going to open the document on Bohr diagrams, and then you're going to open the pen because I'm going to get you to draw it right on that thing. I'm hoping you can do it on your phones. You guys are good at this. So I'm going to try to bring it up here, and if that fails me miserably, I will just write it on the board. I'm catching up to you guys here. Have you found the Bohr diagram sheet? Open it with the pen, and you're going to go to the little box that's on the left. You're going to go to where hydrogen would be on that little blank periodic table. And you're going to draw a Bohr diagram. Put a circle in the middle, not too big, with, and then I'm going to tell you, you're going to put the number of protons in that little circle. That's going to be the nucleus. And you don't even need to put P equals. Just put +1 for the hydrogen one. I'm catching up to you now. See how I'm catching up? I'm a little slow, but I'm catching up. So I can't zoom in the same way as you guys. I don't know if I can make that bigger so that I can see it. Can I zoom in a little bit? A little bit. Actually, I don't want to zoom in because I'm going to have to clear the screen. Oh, I can clear the screen. So, again, I've got someone here that is in the document, but I'd rather you use the pen and open up your own document. Everybody know what I'm talking about there? So in this space here, I want you to put a circle, all right? And I want you to put +1, okay? Then you're going to put an orbit. And how many electrons does this thing have? 1. Put a dot. Okay? you're going to keep on going. Now, I'm going to have to shift over to the other side to get the helium, and my pen marking is going to stay on me. Where's the pen marking? Oh, it's gone. Nice. So for helium, I'm going to put my circle. I'm going to eventually have to make my circle a little smaller. My +1 moved along with me. Don't mind that. What am I putting in the middle of this one? What am I putting in the middle of that one? +2. I'm still dealing with the first orbit. How many dots? How many dots? And how do I want them? I want them together. I want them paired up. That's the new way I want them. 2. Does everybody get the idea? You're going to work your way across. You're going to fill in every one of those. All right? You're going to fill it in for lithium and beryllium and boron. Okay? I'll do a couple more with you. Oh, I got to clear my screen because that's really just awkward, isn't it? See how those are hanging around? Clear the ink. What charge is going in the middle of there? Brett, are you already done drawing lithium? Are you ahead of me? Still on helium? What's the charge going to be in there? +3. Where did that mark come from? See that mark? It magically appeared. That is a terrible plus. There it is. That looks like an F. +3. Didn't work out for me so well. How many orbits in lithium? How many orbits? 2 orbits. You could use different colors if you'd like, because you have access to different colors on that. You could make the nucleus a different color so you don't mix it up. How many dots go in the first orbit? 2. 1, 2. How many in the second orbit? 1. And now we work our way across, filling that second orbit. So we have just wrote a note about the protons, neutrons, and electrons in an atom. And now we're drawing something called Bohr diagrams. You probably did that last year. Unfortunately, as you probably suspect, it's on Google Classroom. And they're zooming in and they're drawing everything nicely on Google Classroom. And unfortunately, everybody's got the iPads. And so I don't have an iPad right now. All right. See if you can fire it up on the phone. What's happening here? Still logging in?
No, like, something's wrong with it. I've signed back in, but I can't fill my student number.
And you don't have your password?
Because I got changed just to my student number. But I don't have a student card.
I'm going to change your password, and then you're going to get back in.
Okay.
Okay. Go ahead. Keep going as I fix this situation. Come up here for a moment. How do I spell your last name? Oops, wrong keyboard. G-I? L-L-A-T-L-Y. You're going to change that password to whatever you want it to be, something that you're going to remember. Then you're going to put the same thing down there. Then you're going to click change password. How's it going? How's it going? So 1, 2, 3. Nice. How's it going here? And why is your screen black? Oh, it's turning. It's turning and turning. Oh my goodness. Here, let me show you something that's a little handy. Watch this.
Oh.
Isn't that a beautiful thing?
Yeah.
I get that pen.
Okay.
Just click on it. It goes
You're gonna,
to your version of here.
Oh, whoa, whoa.
I know how to do it on the iPad. I just
Okay, I gotta pause my video because right now all this discussion is going on my video. So I'm gonna pause it and I'm gonna see if I can fix your issue. And I'm going to make this a regular size. Okay. So, I don't have any pictures on mine, but if we take a look at yours, what do you notice about the number of orbits for the element within the same period? So let's try to answer that question. How many orbits do the atoms have in the first period? How many orbits do they have in their picture? Take a look at your picture. How many orbits? Yep. 1. They both have 1. How many orbits do they have in the second period? How many orbits do your pictures have? 2. How many orbits do they have in the third period? 3. So the period number tells you the number of orbits. That's a handy thing. So down here, under what do you notice about the number of orbits within the same period, you can say it's the same. So just right in there, it's the same. What do you notice about the number of orbits in the same period? It's the same. Okay? Let's see if we can answer the others. What happens to the number of orbits as you move down a group? So, starting with hydrogen, and then you move down to lithium, and then you move down to potassium. What happens to the number of orbits? What happens to the number of orbits? You got your pictures? Are you done? But you don't have a picture in front of your face. All right, that's acceptable. What happens to the number of orbits? What happens there, Josh? It adds an orbit each time. So as you go down to down the group, it increases by 1 as you move down. It increases by 1 orbit. It goes up by 1. Let's look at the others. Again, I got to get rid of the writing because the writing stays in the same spot. And that thing has choked. So I'm going to have to just keep writing. The period number is the same as. So if I'm looking at period 3, yep, it's the same number of orbits. Guys, gentlemen, hey, are you filling in the answers with us as we go? Okay, good. So let's pay attention here. What is the period number the same as? The period number is the same as the number of orbits. So you should be able to determine how many orbits they have just by looking at the period number. I'm hoping I can clear this now. Click. Oh, I'm struggling with clearing my screen. Click. Clear. Yay. What do you notice about the number of electrons in the outermost orbit for the same group? Okay, this is an important thing. So, how many outer orbits does hydrogen, lithium, sodium, and potassium have? How many, outer electrons. How many outer electrons do they have? Yep. 1. Group 1 has 1 outermost electron. How many outer electrons does group 2 have? 2. How many outer electrons does boron and aluminum have? There's a trend here. Even if you don't have your picture, you might be able to tell me. How many outer electrons would these guys have? It's a tricky one because there is a 10 there, but you're going to ignore that. How many do you have in your picture? 3, 4, 5, 6, 7, 8. So, the number of electrons in the outermost orbit is the same as the group number. So you can write that down. It's the same as the group number. Okay? How does this compare? Well, it is the group number. It is the same. So when you draw your Bohr diagram, if I give you something like silicon, okay? Silicon, you can draw then, and I'll write it here on the board. If I give you something like silicon and ask you to write the Bohr diagram, you can tell exactly how many orbits you need and how many are going to be in the outer orbit based on that number. Silicon has 14. There it is right up there in the space, but I'll draw it right there. Silicon has plus 14. How many orbits is silicon going to have? It's going to have 1, 2, 3 orbits. 1, 2, 3 orbits. And now we can draw it without counting them. How many does this first orbit always get? It always gets 2. And it's full. How much does the second orbit always get when it's full? 8. So I can draw 8. 1, 2, 3, 4, 5, 6, 7, 8. And how many outer electrons will it have? How many outer electrons? 4, because it's in group 14. It will have 4. 1, 2, 3, 4. I like them to be on their own, and that's how silicon is drawn. So we can actually now draw some Bohr diagrams without having to go through counting each one. We can draw them in one shot. Okay? All right? Have we got that note kind of written down? We got the information on it? I don't have that necessarily saved with the answers on it, but I could write those answers on a copy of the document and save it on Google Classroom if you didn't quite get it all done because of our charging issues, all right, for you to study, so I can do that. I do have one more thing I want to cover for this. Did you do Google search for a Bohr diagram? That's exciting. Yeah, that's huge. You know, they just put the dots around there. It's not as simple as that. You know what I mean? They represent it to be that simple, but it really isn't that simple. There's a complex way in which they go. That's neat for Francium. Lots of dots. How many in the outermost orbit for Francium, though? Oh, hold on. So what happened was Pat did a Google search just to see what it was like for Francium. Before he even tells us the answer, how many dots in the outermost orbit will this have, no matter how complicated it is? Why? And so how many dots was in the outermost orbit? Is it really? But it's lying. There should be 1. It's wrong. This is why we don't always trust the internet. Is that 2 electrons in the outermost orbit? It's francium. Isn't that supposed to be francium? Yeah, I don't like that. That's wrong. That is not correct. Okay. Let us now exit this for now, and I'm going to go back to my note, and we've done the Bohr diagrams, and I now want to talk a little bit about Lewis diagrams. Just to finish off today, we're going to talk about Lewis diagrams. So Tyson, come back for now. We're going to write this bit of a note. You can leave your phone there. It's not very long. That is the extent of the note right there. And then I've got a second sheet with Lewis diagrams on it, but Lewis diagrams are easier, yes. You're going to hang on to that because in the next little sheet for Lewis diagrams, you're going to need to know where they are. I don't know if you can see that from back there. I know I wouldn't be able to see it from back there. And I will make this bigger so that you guys can see. I'm hoping And I know this is kind of a bit of a mishmash because some of our devices didn't work that great, but I'll do the Bohr diagrams and put it up there so that when you're studying, you can take a look at it. But I'm hoping that some of us got far enough to notice that the outer electrons are the same if they're in the same group. 4 for carbon and silicon, 5 for nitrogen and phosphorus, et cetera, et cetera. It turns out when it comes to chemistry, the outer electrons are the most important electrons. It's only the outer electrons that participate in chemistry and do things. So it's only the outer electrons we're interested in. So drawing all those circles with all those extra dots on the inside is not a useful thing to do. We only want to represent the outer electrons, just the ones in the outer shell. Remember I told you I wanted you to put the dots kind of like they were on a clock? That's because that's the way we do it in a Lewis diagram. And that's representing how chemical reactions are going to happen. That's why we were preparing you for it. You can imagine the symbol having 4 sides, like on a clock, 12, 3, 6, and 9. Each side can hold a maximum of 2 electrons. First we put them by themselves, then we pair them up when we have to. The valence electrons, another way of saying the outer electrons. Valence is a word that comes from a word that means to be powerful, right? If a Norse Viking, when he dies, does anybody know where the Vikings believe that their dead warriors go? Do you know where they go? Valhalla. And the term valence comes from the same root word as Valhalla. It means to have power. So valence simply means the power to form bonds with other atoms. So the outer electrons are what determines the power of an atom to bond. That's where it comes from. Let's draw some Lewis diagrams. They're very simple to draw. So at this point, I'm not gonna make reference to this. I'm gonna go back to my sheet, which is now a second sheet that you guys have on Google Classroom, and that is on Lewis symbols. Again, open it up so that you can write on it. Okay? And this time we're going to do the Lewis symbol, and I'll go through a few of them with you. I'm going to see if I can squeeze them right in there. So here's how you do the Lewis symbol. Number 1, you put the element symbol as the center. Because the element symbol tells you really what the element is. And then you put you're going to you want to push the pen, so go back. And again, you're going to open it. And then you're going to, when that pen presents itself, you're going to click on that pen, and then you can write on it. It's in group 1. It has 1 electron. Some people use dots, some people use X's. I like dots. Or X's, it doesn't matter. Helium is a special case. It's in group 18 or 8, but it only has 2 outer electrons. You can go grab your device, see if you got enough juice to finish this up. Lithium. Again, I'm only drawing outer electrons. How many outer electrons does lithium have? What group is it in? So, 1 dot for lithium. They will look all the same in the same group. So instead of me moving over, I'm going to move down to, what is next? Sodium. Sodium is also in group 1. So how many dots will sodium get, Brett? 1. 1 dot. I'm going to move down again to potassium. Also in group 1. How many dots?
30.
No. 1. Your sarcasm is indicating to me that you get it. I like it. Beryllium, Be. Now here's where it's a little different. How many dots for beryllium? How many dots? What group is it in? Give a rest. Have a rest. How many dots? Brett? 2. But this time we don't pair them up. 1, 2. You could put them on opposite sides. That's okay. But don't pair them up until they have to be paired up. I could work my way down and I could put 2 dots in for the rest of these, but now I want to work my way across to illustrate what happens as we go across. We're going to miss the transition metals. We're going to jump over here to 13. I've got boron. How many dots? How many dots? Pat, how many dots? 3. Not 13, but 3. Don't pair them up yet. 1, 2, 3. Carbon. How many dots? Jacqueline, I don't know whether you've caught up to us. How many dots for carbon? It comes from the group number. We're ignoring the 1. Nope. Here, take a look here. Take a look here for a minute. 1, 2 dots. Ignore the 10. 3 dots. 4.
I didn't know that figure out.
Yeah, that's the number that was at the top. That's what that number is. That's the group number. Ignore the 10 because we're not worried about these guys in the middle. Now, that brings me to nitrogen. How many dots around nitrogen? Max, how many dots? Take another look at location of nitrogen. 5. So, yeah, this is, I've shifted over a little bit. It's this box here. So here's the way it looks. 1, 2, 3, 4, and where am I going to put the 5th one? Next to the first one. They start to pair up. They start to pair up. Oxygen, 1, 2, 3, 4, pair, 5. Oh, that's really close together. Pair 6. I apologize for that one pair. I can't fix it because my eraser doesn't work. Fluorine. 1, 2, 3, 4, 5, 6, 7. When we pair them up, we call them pairs. Fluorine has 3 pairs and has 1 lone electron. 3 pairs and 1 lone electron. When we start talking about bonding, fluorine is going to look for an extra electron to fill that pair, because atoms like to have pairs of electrons. Yeah, question?
What is only up to?
Because the first orbit can only hold 2. It's simply the laws, well, it's the laws of quantum mechanics. I used that big word earlier on. Quantum mechanics are the physics rules that govern the way atoms behave. Very, very complex. I took it in university. I took 2 courses in 3rd year and 4th years at university. Mathematics that would just blow your mind. If I go back and look at my notes now, my mind is blown. I can't even remember how I did the math that long ago. But simply the laws state that the first one can only have 2. Okay, it's just the way it is, unfortunately. And then neon. 1, 2, 3, 4, 5, 6, 7, 8. Everything's paired up. That's a happy atom. It's got 8 electrons. Okay? We've got 5 minutes left. You can complete your pictures. Okay? They're going to have the same number of dots for the group. And in terms of these answers down here at the bottom, what trends do you notice about the Lewis diagrams for group 1 group? It's the number of dots. Group 1 has all 1 dot. Right? Group 2 gets 2 dots. Group 3 gets 3 dots. So I'm not even going to worry about that. You can write that in if you'd like. Okay? All right? And I'm going to stop my video there, and you guys can complete can keep working on those two, the Bohr diagram sheet and the Lewis diagram sheet. Let me just finish my video, and then I'll be there in a second.